Assalamualaikum warahmatullahi ta'ala wabarakatuh. Welcome to another video on MCTE 2311 Signal and System Analysis. In this video, I will show you the solution to question number 2 on modeling of a mechanical system. So here you are given a mechanical system with mass, spring and damper where there are two masses M1 and M2 and they are connected through this damper B3 and spring K2. X1 and X2 are the output of the system, which is the displacement of M1 and displacement of M2, and F of T is the input, input force applied to M1. Now, in order to determine the differential equation that represent this system, we have to find the equation of motion for M1 and M2 separately. And we do that by first, say for M1, first draw the free body diagram of M1. So here M1 we have input F of T, which is force applied to the mass, and the output is X1 of T, which is displacement. Now the next thing to draw is the reaction forces. So first we have reaction force due to K1, which is multiplied by displacement. Okay, this one is available in the slide, okay, that I show you. Yeah, I discussed about this in the video as well. So if we apply this force to displacement relationship, we have this K1 X1 of T. Now we have another reaction force which is due to the mass itself, M1, which is equivalent to d square X1 T over dt square, mass multiplied by acceleration. Next one we have due to the due to the friction B1, which is equivalent to B1 multiplied by displacement. Okay, next we have reaction force due to B3, and we see this B3 here, okay, is connected between two moving masses M1 and M2, and here we are modeling M1, so we will have B3 dx1 minus dx2. Here we have K2. Then similarly, K2 is connected in between M2 and M1, which are both moving masses. So here K2 multiplied by X1T minus X2T. And note that all reaction forces direction are opposite to the direction of motion, because the reaction forces is opposing motion. So next step is to write the equation of motion, which is the differential equation to represent this system. So we will have M1 d square, sorry, this one is X1 of T over dt square plus, now I have here multiplier for X1. The X1 here is multiplied with B1, and here X1 also multiplied by B3. So I can write here B1 plus B3. And then minus, because here I have a minus sign over here. Multiplier is B3, this is dx2. Plus for k, we have k multiplied with x1, and here we have k2 multiplied with x1 as well. So we will have k1 plus k2 x1 of t minus k2 x2 of t equals to the input force f of t. So let's call this equation 1. So this is the first differential equation that represent M1. So to find the differential equation that represent M2, we have to again draw the free body diagram of M2 with all the reaction forces. If I bring this up a little bit, we will have here M2 and the displacement is x2 of t. Okay. For reaction forces, here we have 1 due to B3, and this time we are modeling M2. So we have the x2t minus dx1 of t, and over here we have k2, which is x2 minus x1. Here we have this spring k3 x2. We have here the friction B2 and lastly another reaction force which is due to the mass itself. Right, then we write the equation of motion, okay, by applying summation of force equals to 0. So here we have M2 d square x2 plus I have here B2, B3 and B2 multiplier for x2. So let's write B2 plus B3 dx2t over dt minus B3 dx1 plus we have k2 multiplied with x2, and you also have here k3. So you have k2 plus k3 multiplied with x2 minus k2 and x1. This time it's equals to 0 because no input is applied to the second mass. So let's call this equation 2. Okay, so now these are the differential equation that represent the system, okay, which is equation number 1 and equation number 2. Okay, so I will see you in the next video where I will show you the solution to question number 3. Thank you.